All right, welcome. In this video, we're going to talk about rational functions. We're going to talk about what kind of function that is, and we're going to talk about kind of analyze all of its important parts, including asymptotes and the whole, the possibility of a whole. Okay, so let's get started. A definition, a rational function, this is a function of the form p of x over q of x, where the p of x and the q of x represent some polynomials. We're going to divide two polynomials, and anytime we divide, we want to make sure that the denominator does not equal 0, since we can't divide by 0. So q of x, no matter what polynomial that is, should not be 0. Okay, there are a couple of basic graphs that we could look at. I'm just going to take the time to look at 1 over x. 1 over x squared would also be another good basic function that you could think about and take some time to delve into. I'm just going to use the 1 over x today. Okay, so to start out, you can think about what number for x is not going to work based on what we just said, right? We can't divide by 0, so x cannot be 0. So what that does is that gives us a place where the function is undefined. We don't have a point there. We don't have the curve cannot hit that spot where x is 0. And so we kind of have this dividing line that divides it into two curves. So to get points on either curve, when I make a graph, I usually put that value that doesn't work right in the center. And I just mark that it's undefined there. I want to show you what happens around 0. So I've picked a lot of interesting x values here. If I were making this graph for myself after I've gotten the idea of the shape of what this looks like, I may not need all of these points, but I wanted to show you some of the activity around 0 and at the ends of the graph where x gets really big. Okay, so if we have a place where x cannot, a value that x cannot be, it divides the graph up, and we often draw a dotted line to show that. It's called a vertical asymptote. So the vertical asymptote for this graph is where x is 0, which is right on the x-axis or the y-axis. I'm going to do VA for vertical asymptote, and that's the place where x is 0. Okay, if we thought really hard about the numbers we could get out of this function, I can put any other number in for x, just not 0. When I put in really large numbers, like 1,000, we're going to plug that in a second, 1 divided by 1,000 is going to be a really small number. If I make it even bigger, like 1,000,000, 1 divided by 1,000,000 would be an even smaller number. And it's going to continue to get smaller and smaller. But just because of the way I'm calculating this, it's never going to actually end up to be 0. And the only way that a fraction can be equal to 0 is if the top is equal to 0. So the y value is also never going to be 0. And so there is a horizontal line that we could draw right here on the x-axis called a horizontal asymptote. And the reason why we draw in these dotted lines, they're not actually part of the graph itself. They are kind of like guiding lines to help us draw the graph, because the curve is going to get infinitely close to these lines. So let's use our t-chart to kind of show you how and why that happens. So I want to plug in a couple points around 0, and then I want to see what happens at the end. Let's start out with the positives. So when I put in 0.001, 1 divided by that little tiny number gives me 1,000. 1 divided by a half, there are 2 halves in a whole, so it's going to give me 2. 1 over 1 is 1. 1 over 2 would be a half, or 0.5. and 1 over 1,000 is going to give me a really small decimal, 0.001. So on the right-hand side of the graph, I could plot these. This is one curve. Okay, so when I get, let's do these three in the middle first. Those are the most appropriate points to plot. So 1/2, I'm at a y value of 2. I have the point 1, 1, and I have the point 2, 1/2. As x gets really close to 0, 0.001, the y value is getting really large. So as x gets really small, y gets really large. It never actually touches the y-axis, but it gets infinitely close. As x gets really big, the y value gets really small. So as we go to the right, kind of approaching infinity, the y value is going to get smaller and smaller and smaller. It's never actually going to touch the x-axis, but it's going to get infinitely close. Same thing happens on the negative side of the graph. So if I put in a negative 0.01, I'm going to get negative 1,000. This is going to give me negative 2, negative 1, negative 1/2 or 0.5, and negative 0.001. Okay, so if I make x negative, y is also negative, which means I'm over here in quadrant 3. These 3 points in the middle are the easiest to plot. So I've got negative 2, negative 1/2, negative 1, negative 1, and negative 1/2, negative 2. And the same pattern is happening. As I get really close to 0, the y value is getting really large, this time in a negative way. So it's going to get infinitely close to the red dotted line that we drew there. At the end of the graph, when x gets really large, y gets really small. It's negative, but it's getting close to 0 from the bottom. Okay, so this describes the patterns in this type of rational function. The way it approaches these dotted lines and it kind of levels off at the ends like this. We could list out the domain and range for this graph. So remember we said that the x value was not going to be 0. So the domain, if we were to draw a number line, we're leaving out 0, but we're including every other number as a possible x value. So the domain goes from negative infinity up to 0, but not including 0, just infinitely close. We use the parentheses to show that. And then we're skipping the number 0 and starting just after infinitely close from 0 to infinity. And that should match up with the graph, right? From negative infinity up to 0. And then from just after 0 on to infinity. Okay, the same thing's true about the range. For the range, the y value is not equal to 0. So we could say the same thing. This is bottom to top, but vertically, we're going to go from negative infinity up to just under 0, skip the number 0, and then on the other side of the curve, just after 0, up to infinity. So down from negative infinity up to just below 0 over here on the left, then just after 0 on the right, all the way up to infinity. Okay, so let's take a look at, we can take these graphs and apply transformations just like we talked about for all the other graph shapes. So I want to take a second to look at that with you for a minute. Okay, so this is a transformation using 1 over x. And we've talked about these a little bit. The inside of the function is the denominator for this one. So on the inside I have a -1, which means this one is shifted right by 1. And on the outside I'm shifted up by 1. When I shift the graph, I also move the asymptotes. So the x value that's not going to work for this function is 1. Because 1 minus 1 would be 0. So in the center, at 1, my function is undefined. And to make a good graph, it would be good to choose some x values around 1 so that I have points that I can plot. Let's go ahead and draw in the vertical asymptote at 1. Since this graph is shifted up by 1, normally the vertical asymptote or the horizontal asymptote is on the x-axis, but now it's been shifted up by 1. And as x gets really big, this fraction here gets really close to 0. 0 plus 1 means my y values at the end are now going to approach 1 instead of 0. If I plug in some numbers, so if I plug in -1, I'm going to have -1/2 plus 1, so 1/2. If I plug in 0, I'm going to have -1 plus 1, which gives me 0. If I plug in 2, I'm going to have 1 plus 1, which gives me 2. If I plug in 3, I'm going to have 1/2 plus 1, which is 1.5, or I guess I'm going to mix formats and do 1.5. Okay, however you like to represent that. 3/2 would be good too. So if we plot those, we have -1/2, 0, 0 on this side. This is one curve. We just picked a couple of points because we kind of already know the shape. We could plot more, but we know that at the end it's going to approach the horizontal asymptote, and in the middle it's going to approach the vertical asymptote. The same thing would be true on the right-hand side. We have the point 2, 2, and the point 3, 1.5. The curve is going to approach the vertical asymptote in the middle and the horizontal asymptote at the end. Let's try another one of these. I wanted to do one like this because it's kind of an interesting way of viewing this. It's difficult to see the transformations with the function written like this, but if we rewrote it in a different way, we would be able to identify it a little easier. So we could rewrite this as x minus 3 plus 1 on the top. All right, notice I haven't changed anything. This -3 and +1 are going to add to the -2 that I have here. Can you see why that might be an advantage? Because now I can divide both of these things by x minus 3. X minus 3 divided by x minus 3 is going to give me a 1. And then I have 1 divided by x minus 3. Okay, and I can identify the shifting here. So this one has been shifted right by 3 and up by 1. The 1 is written in the front. I could also have written it in the back so that it looks more consistent with what we've done in the past. Because it's undefined at 3, I want to put that in the middle of my t-chart and choose a couple of x values around it. So my vertical asymptote is going to be at 3. Just like the previous one, as x gets really large, this fraction is going to go to 0. 0 plus 1 means my graph is going to level off at 1 at the ends. Okay, so if we plug in some points, it doesn't matter which function we use, whether we use the original or whether we use this one. It really doesn't matter. Okay, I'm just going to use the one we reduced. So if I plug in 1, I'm going to have 1 plus negative a half. So that's a half. I'll use 0.5 this time. If I plug in 2, I'm going to have 1 plus negative 1. So 0. If I plug in 4, I'm going to have 1 plus 1. And if I plug in 5, I'm going to have 1 plus a half. Let's plot those. Remember, these two curves are going to approach the dotted lines. The vertical asymptote in the middle and the horizontal asymptote at the end. Okay, so this is one way, by using transformations, we can graph rational functions. Now let's talk a little bit about what the asymptotes are and how we find them. Let's do them one at a time. So the first type of asymptote is a vertical asymptote. This is a vertical line which the graph approaches but does not cross. Vertical means up and down, right? To find the vertical asymptote, we're going to factor and reduce the fraction. The reducing part is very important because anything we cancel out is not a vertical asymptote. Then we're going to set the denominator equal to 0 and solve for x. Because it's a vertical line, it'll be x equals some number that represents the vertical asymptote. Okay, next we have the horizontal asymptote. This is a horizontal line which the graph approaches at the ends of the graph. So the horizontal asymptote is sort of like the end behavior for these graphs. If they level off, sometimes they do and sometimes they don't. Because it's a horizontal line, it'll be a line that looks like y equals some number. And because these graphs can have multiple parts, a graph may cross its horizontal asymptote. Usually that happens somewhere in the middle. Because it's the end behavior, really the horizontal asymptote is not something that governs the function in the middle. It just governs it at the end where x goes to infinity or negative infinity. So it's possible that it could cross the horizontal asymptote. There are two ways to find the horizontal asymptote. One is to use this three-part rule. I found that many people like this method, so I usually use this in college algebra. But there is another method that you can use as well, so it's just a matter really of your preference at this point. The three-part rule is a little bit of memorization, so there's that, whereas the second method here is more of a process that you could carry out. Maybe there's less to memorize there. I don't know. I'm leaving that up to you. Okay? So there's three possibilities for this three-parted rule. We're going to compare the degree or the highest power on x in the numerator versus the denominator. And depending on which one is higher, it's going to dictate whether or not we have a horizontal asymptote, and if so, where does it level off? If the degree of the numerator is higher, that means the highest power of x is on the top, then as x goes to infinity, oh, I'm sorry, I read this wrong. That would be this one, wouldn't it? I guess we'll go from bottom to top. If the degree of the numerator is bigger than the degree of the denominator, then as x goes to infinity, the numerator is going to grow faster. And it's going to grow kind of in an unbounded way so that nothing's restricting it. And it's not going to level off. So in that case, we don't have a horizontal asymptote. If the degree of the numerator and the denominator match, so we have x squared on the top and x squared on the bottom or something similar to that, then it is going to level off at some other non-zero number. So to calculate where it levels off, we're going to take the leading coefficient, the number in front of the highest power of x on the top, divided by the leading coefficient in the bottom. And this will give us the horizontal asymptote, and it will tell us where the graph is going to level off at the end. If the numerator degree is smaller, so if the exponent in the numerator is smaller than the denominator, in this case, I think of the denominator wins, right? It has the higher power. That means the denominator is going to grow faster as x goes to infinity or gets really large. And if the denominator grows faster, then the y value gets really small, like a lot of the examples we just graphed. So the y value is going to level off at 0. Your second option is to take your fraction, not factored, regular, expanded out, and divide the numerator and denominator by the highest power on x. So you look over the entire fraction, find the highest power, and divide everything in the fraction by that highest power. Once you've done that, you're going to allow x to get really large because the horizontal asymptote affects the ends of the graph. And anything that looks like 1 over x to some power is going to go to 0. And anything else may level off at some number. Maybe the powers of x cancel out. Okay, so then you could evaluate which of these scenarios are going to come out of that. And you don't have to remember these because you will be using this process to figure out where the y value is leveling off. So you're calculating it rather than memorizing the pattern. Okay, so that's the horizontal asymptote. Then the last one would be the case where we have a hole in the graph or a missing point. So if a rational function can be reduced as a fraction, the eliminated factor yields an x value that's not part of the domain and causes a missing point or an open hole in the graph. To find the hole, we're going to set whatever we've canceled, the eliminated factor, equal to 0. This is going to give us the x value. And then because we want to plot this hole, I should say the hole will be in line with the rest of the curve. We would like to plot it. So to plot it, we need both an x value and a y value. We're going to plug x into the reduced function to find the y value. If we were to take that x and go back to the original function, there's a problem there. That's why it's a hole. We would get 0 over 0, which is something that we can't calculate. Okay, so let's try these out, these three things. Here's an example from your book. Okay, so maybe it would be good to factor this first. The top is a difference of 2 squares. And we can factor the bottom. Okay, notice we're able to cancel out. That lets us know right away that we're going to have a hole. Anytime we cancel, we're going to have a hole. Okay, so we have factored and reduced. To find the vertical asymptote, we're going to set the denominator equal to 0. You could probably do this in your head. Okay. So the vertical asymptote is at x equals 3. For some reason, I did not put the horizontal asymptote next. I'm not sure why. Okay, I guess we'll just follow along with what we have here. So the hole is going to come from whatever we've canceled out. Notice we've canceled out on the x minus 1. So we want to set that equal to 0. That means we're going to have a problem spot at 1. And we'd like to have some coordinates so we know how to plot this missing point. So we want to take the 1 and plug it into the reduced function to get the y value. So if I do that, I'm going to have 2 divided by -2. So the y value will be at -1. So altogether, that means I have a hole at the point 1, -1. Okay, and I would like to point out that any factor I have in the denominator is going to be one of these two things. If it remains in the denominator, it will be a vertical asymptote. If I've canceled it out, it will become a hole or a missing point. Then we have the horizontal asymptote. So if we use the 3-part rule, let's do that first. And it doesn't matter where you look, whether you look at the original or the reduced, they're going to give you the same result. So we're going to compare the highest exponent on the top versus the highest exponent on the bottom. So in this case, they match. They're equal. If they're equal, they're going to level off at some non-zero number. To calculate that number, we take the leading coefficient, so the number in front of the highest power on x, that was supposed to be a 1, and the number in front of the highest power of x on the bottom. So 1 over 1, and we could do the same thing here, 1 over 1. So our horizontal asymptote will be at 1. Okay, just to show you both options, let me redo that with the second method. This method would take this function and divide by x squared, which is the highest power on x. So that's going to give us x squared over x squared minus 1 over x squared in the top, x squared over x squared in the bottom, minus 4x over x squared, plus 3 over x squared. Okay, all of these, I'm just going to circle them. As x gets really large, they're going to go to 0. And these two, because they cancel, are going to give us a 1. So really this, as x gets really big, this approaches 1 minus 0 over 1 minus 0 plus 0, which is 1, right? So we get the same result if I do this method or the 3-parted rule. All right, so we've now found the vertical asymptote, the horizontal asymptote, and the hole. So to make our graph, we want to put that information on the graph. So we'll start with the vertical asymptote at x equals 3. Then we have the horizontal asymptote at y equals 1. If you want to go ahead and plot the hole, our hole is at the point 1, -1, which is right here. Okay, and we would like to fill in the graph with some other points so we can get a good idea of where the curve is. Just like before, I usually put the vertical asymptote in the middle, so I'm guaranteed to get points on both sides. 2 would be a good one. We already have 1 because that's our hole. 0 would be good. And actually -1 would be good. Let me put the function over here again. -1 would be good because it makes the numerator 0. And so that's going to be 0 over -2. That's an x-intercept. 0 would be good because that's going to give us a y-intercept. This one would be -1/3. It's not perfect. It's not a whole number, but that's okay. 2 would give us 3 over -1, so -3. Okay, so on this side of the graph, I have a couple of points I can plot. Now you definitely don't have to plot that many, but I just wanted to include those intercepts because those are really good points to help you out. And they're going to approach these dotted lines, the vertical asymptote in the middle and the horizontal asymptote at the end. Then don't forget the other side, so we would like to choose a few points on the right. So if I put in 4, I'm going to have 5 over 1. If I put in 5, I'm going to have 6 over 2. So 4, 1, 2, 3, 4, 5. And 5, 1, 2, 3. And just like before, it's going to approach these dotted lines. That's why we've drawn them there. Okay? Let's add to this conversation a little bit. So there's one more type of asymptote that we're going to be working with, and that's called an oblique asymptote. This is a slanted line that the graph approaches at the ends of the graph. It's a slanted line, so it's going to have a form that looks like y equals mx plus b. Just like any other line that we may have graphed in the past, okay? To find the oblique asymptote, there's a criteria. The degree of the numerator must be 1 more than the degree of the denominator. And so we're going to be dividing the numerator divided by the denominator. For our class, we're going to use synthetic division for that, which means there's really only one scenario where the top would be x squared and the bottom would be x to the first that we would be using because we're going to be doing synthetic division. Any other scenario where the numerator is 1 more than the denominator would require polynomial long division, which is possible to do as well. So we're going to divide, and then we're going to disregard the remainder, and the quotient that we get is going to give us the m and the b. So let's try this out. This is number 62 from your book in this section. So let's walk through all the parts. The vertical asymptote is going to come from setting the denominator equal to 0. Notice we didn't have to factor. This top is really not factorable this time, so that's not a concern. The horizontal asymptote, if you think back to the 3-parted rule, if the numerator is higher than the denominator, then it's not going to level off. As x gets really big, the numerator is going to grow uncontrollably and go to infinity. So there is no horizontal asymptote. The graph will never have both oblique asymptote and horizontal asymptote. It's always going to be one or the other. So the ends of the graph are either going to approach a horizontal line or it could approach a slanted line, but not both. Okay, because we did not factor or cancel, we have no hole for this one. Now let's find the oblique asymptote. We want to divide the numerator divided by the denominator. We're going to use synthetic division for that. Notice in the numerator we do not have an x term, so we need to leave a gap for that. So we have 1 for the x squared, 0 for the x, and -5 for the constant. We're going to bring down the 1, multiply by 3, and add down. Multiply by 3, and add down. Remember, the numbers at the bottom are going to go down by 1 power of x. We were at x squared, so now we're going down by x to the first. So this is the coefficient in front of the x. Actually, this is the m. And this is the constant, which would be the b. Remember, we said we're going to disregard the remainder. So our oblique asymptote is the line y equals x plus 3. Let's plot this on our graph. Let's start with the vertical asymptote at 3. Okay, and then we need to maybe come up with some points off to the side where we can use to plot this slanted line. The x and y intercepts work really good for this. Okay, so -3, 0, and 0, 3. And we need to go pretty far out, so you could even pick some more. I'm going over 3 and up 3. Over 3 and up 3 might help you make it straight. Okay. There we go. So this is our oblique asymptote. All right, and then we need some extra points to plot. So we'll pick some x values. I'm going to use the same procedure. I'm going to put my vertical asymptote in the middle and pick a couple of points smaller and a couple of points larger and plug them in. If I plug in 1, I'm going to have -4 over -2, so that's 2. If I plug in 2, I'm going to have -1 over -1, so that's 1. If I plug in 4, I'm going to have 16 minus 5, that's 11 over 1. And if I plug in 5, I'm going to have 25 minus 5, that's 20 over 2, so that's 2. Okay, so I have the point 1, 2, the point 2, 1. If I plugged in 0, I'd have 5/3. That's like 1 2/3, so it'd be right about here. And if I set the numerator to 0, I'm not going to work that out on paper, but I would get the square root of 5, the positive square root of 5, and the negative square root of 5, which is like 2.2 something. Okay, so that might help you draw this. It's also going to be approaching these dotted lines. That's why we have them there. So it'll look something like that. On the right hand side, we've got 4, 11, and 5, 10. And it is also going to be a curve that approaches these lines. So it'll look something like this. All right. So I hope that gives you a good idea of how the oblique asymptote works. I would love to do one more with you so you can see a graph that has more than one vertical asymptote. Okay, so this one's already factored. So setting the denominator equal to 0, I think you can probably do that in your head. We're going to get 2 vertical asymptotes, x equals -3 and x equals 4. The horizontal asymptote, if we were to multiply this out, the highest exponent in the top would be x squared. The highest exponent in the bottom would be x squared. Now you could pretty easily FOIL this. I'm not going to do that just in the interest of time. I'll just do this. Okay, so if they match like that, then we take the numbers out front. So the y is going to level off at 1 at the ends of the graph. Okay, do we have a hole? No, because we didn't cancel. Do we have an oblique asymptote? No, because the numerator does not have a power that's higher, one higher than the denominator. Okay, so just these. So let's start out with the asymptotes. So I have a vertical asymptote at -3. I have another vertical asymptote at +4. And I have a horizontal asymptote at 1. Okay, so I need to choose some points to go around this. And I don't have a middle anymore because I have 2 vertical asymptotes. But I want to make sure I get points that are around -3. And I want to get a couple points that are around 4. I'm going to put it down here. Maybe add a couple spots at the bottom. Okay, so -2 and you know what? Let's use the x-intercept, -6. That'll make a nice point. Okay, and then bigger than -3. Let's see. I would normally do, oh, I put -2 on the wrong side. Sorry, let's make that -4. Let's put -2 on this side. 0 give us the y-intercept, and then the other x-intercept is going to be at 2. So that would be a good choice. Maybe a couple numbers bigger than 4. Right, that looks like a lot, but hopefully some of them will be pretty easy. -6, because it makes this 0, is going to make the whole fraction equal to 0. If I plug in -4, I'm going to have 2 times -6, so that's -12 over -1 times -8. So 8. So 12 over 8 would be -3/4, 3 halves, 1.5. All right, if I put in -2, I'm going to have 4 times -4, so that's -16 over 1 times -6. So -16 over 6 would be the same as 8 over 3. Yeah, I probably should have done these ahead of time. Okay, if I plug in 0, I'm going to get -12 over -12, which is 1. If I plug in 2, that's my other x-intercept, so that's a really nice point. Okay, the others here don't come out even either, so I'm just going to put this down because I don't want to make you listen to me do it in my head. Apparently I did this earlier and I plugged in 5 and I got 4.1. I plugged in 6 and I got something like 2.6. Okay, and I'm not feeling confident about this one, so we'll double check it. All right, so -6, 0, -4, -1.5. So this is one curve. Okay, it's going to approach horizontal asymptote at the end, vertical asymptote in the middle. Let's do the right-hand side and we'll come back to the middle, okay? 5, we're at 4.1, about right there. And 6, we're at 2.6. Same thing's true. Horizontal asymptote at the end, vertical asymptote in the middle. Okay, this middle section can look any kind of way, so you do have to kind of be careful. We know that we have a point at 0, 1. So this graph does cross its horizontal asymptote here in the middle, and that's okay. We have a point at 2, 0. And then let's double check this one. So if I put in -2, I'm going to have 4 times -4. So that's -16. And then if I put it on the bottom, I'm going to have 1 times -6 over -6. So I thought this one might have been positive. So that's positive 8/3. So that would be -2. 8/3 would be 2 and 2/3. So about right there. Okay, you could definitely add more points, but this graph is going to approach the vertical asymptote over here on the left, and this vertical asymptote over here on the right. So we get a picture that looks just like that. I hope this gave you a really thorough look at rational functions. I hope that you have a good idea of what each of these asymptote types look like and how to find them. So good luck, practice, and we'll see you in the next video. Thanks.